Hello and welcome to the fourth lecture on PDEs. So before we go on to describing what we want to do in the lecture today, let me just remind you of this general method that I told you about last time around. And what I said last time around is that when you're given a smooth boundary condition, when you're given this uh, Cauchy boundary conditions on a smooth curve C, and you are to determine, how to evaluate a general equation like this in 2 dimensions. So we had a way of trying to do this, and this boiled down to, trying to uh, understand what would entail trying to solve this when this was when we had an analytic function in x and y. So by that we meant we had an expansion. We had a function of n real variables psi, uh, which can be and uh, Taylor expanded about a point x1 not to xn in this n dimensions. Now, for our case, when we're looking at 2 dimensions, this just meant that, this psi of xy, the one that the differential equation is supposed to, we are supposed to solve and get the thing for, that can be expanded in terms of psi at the point x naught, y naught, and this various, various all derivatives of psi at the point x dot y naught. Okay. And what we saw is that once we are given these, once we are given these boundary conditions, we can actually find out all of these psi x, psi y, and any arbitrary sort of derivatives of psi. So this is what we went to try and see. Um, so we broke this up into things like the uh, I mean tangents and the normals at this point, and we had parameterized the smooth curve as something, and we got everything in terms of that. So everything was known. So we at first tried to find out what psi x and psi y were, and these were given in terms of this del psi del n and psi prime as well, which was the uh, t times the grad of psi. And these determined psi x and psi y, right? Because these things are this, this, so hence psi x and psi y are known. Okay. Similarly, so yeah, so that's how what we did is we were able to find out these uh, first order derivatives, and then we could look at second order and third order and so on and so forth. But let me just also remind you that what you were given is uh, psi xy at c, which was a of xy, and del psi del n at c, which was b of xy. So if you give me psi of xy, then we would also know that tangential derivative which is this unit tangent at a point c dotted with the grad of psi. Very good. So that's what we know, and we can then determine psi of x and psi of y. Sorry, we can determine psi of x and psi of y. And then what we wanted to do is we wanted to move on and find out what second order derivatives. And what we what are the things that we used out here? We used the PDE, and where you plug in s equal to s naught, and you find out what. So this equation, when you plug in, I mean so x equal to x naught and y equal to y naught, that becomes a known quantity, and you have the knowledge of del s of psi of x that you know from here, so you know psi of x, you know psi of y, and then you can find out del f of psi of x and del s of psi of y, and hence all of these things are known. So what you figure out is that, when you write down this as as a vector, so the matrix that, this guy is equal to a known vector. um, Rather, the left hand side is equal to some known vector. Okay, so you would be able to solve for psi xx, psi xy, and psi yy if the determinant of this is not equal to 0. Okay, so the question, and again, what we did for the third order things, again, we saw the same thing, is that this again makes its reappearance in the third order things as well. And if you go on higher and higher, you will find out that this is always the case. So this delta, which is equal to the determinant of this matrix, this equal to 0, seems to be something very important. The question that we are asking in this class that we are going to be doing today is, what exactly is this equation? What does that have to? How does that help us solve our equations? Okay. So this is what we are asking. So let's start off, and this is going to be something called characteristics. So so let's start off by saying wish to understand. The implication of uh, delta equal to 0 in the Cauchy problem. Okay, so remember that delta is what? Delta is given as y primed s naught a minus twice x primed s naught y primed s naught b plus x primed s naught squared c. So this has to be a squared as well, I'm sorry. This being equal to 0. Okay. So at s equal to s naught, this equation is related to the slope of the curve uh, at slope of the curve c at x naught y naught. So okay, so let's write this down again. At s equal to s naught, equation is related to the slope of the curve c. So that is, dy dx at x naught y naught is equal to y primed s naught by x primed s naught So, you know, just from here, this is just dy dx squared a minus twice dy dx b plus c is equal to 0. That essentially means that dy dx is just given by b plus minus root over b squared minus ac by a, right? So now for each sign, there is a plus minus sign out here. The above equation determines a differential equation that has to be solved, okay? And the solution to each equation uh, contains an arbitrary constant. So a priori, this would lead to two families of curves, and these are the curves which are going to be called characteristic curves, okay? Let's so solution leads to two families of curves, and families of curves, these are called characteristic curves or characteristics. Now for a hyperbolic, no, now let's just you know uh, figure out what this is. A priori, you would have that these two characteristics pass through x naught, y naught, and they should be real and distinct. Remember that for a hyperbolic equation, PDE, b squared is minus ac is greater than 0. So the square root is real. So characteristics are meaningful, physically meaningful. Characteristics are in the real plane and physically meaningful. For an elliptic PDE, b squared minus ac is actually less than 0, and square root is purely imaginary. So solutions don't lie. Solutions don't lie in real space. And these are not so useful anymore. And for a parabolic equation, b squared minus ac is equal to 0. And what happens is that there's only one solution. one equation for characteristics. Okay. Now from this we can see that the usefulness of the method of characteristics is relatively limited to the hyperbolic sort of PDE. For the elliptic type, we would need some alternative methods to solve this, although characteristics would remain useful in a formal sense. Now, what we have done is we have found that all coefficients of the, so what we have essentially found is all the coefficients of the Taylor expansion that I just told you about, from the previous class. So that remains, that is going to be determined at a point on this curve C if the curve C is not parallel to a characteristic at that point. Okay. So assuming that the solution is analytic, the solution can then be determined in some neighborhood. Again, if C is nowhere parallel to these curves. So let me write this down. All coefficients of Taylor expansion can be determined at a point on C if C is not parallel to a characteristic. At that point. And so solution can be determined in some neighborhood of C of each point on C if C is nowhere parallel to a characteristic. Okay, so let's try to find out what the characteristics of some equations are. So let's go back to the family of, so let's look at our family of equations again. So del 2 del x squared plus del 2 del y squared acting on psi is equal to 0. Let's start off with this. So what is that? So in this case, A is equal to C is equal to 1, B is equal to 0. So what is happening is B squared minus AC square root of this is equal to minus 1. Rather, no square roots, I'm sorry. B squared minus AC is equal to minus 1. That means, so this is an elliptic equation, as you can understand. So elliptic equation equations for the characteristics are simply, so characteristics are simply dy dx is equal to plus minus of I, which essentially means that x plus, y plus ix is equal to some c1 and y minus ix is equal to some c2. So these are formal equations. So the characteristics of the c1 and c2 are arbitrary constants. And so characteristics through x naught, y naught are given by y minus y naught is equal to plus minus I into x minus x naught. So that's the first equation. Let's look at the second equation, del 2 del x squared minus del 2 del y squared psi is equal to 0, our other fun equation that we had before. So here this is fine. So b squared. So here this is b squared minus ac is equal to 1. So this is a hyperbolic equation, as you know, hyperbolic PDE. And the characteristics are given by x plus y plus x equal to c1, y minus x equal to c2, and so okay, dy dx is equal to plus minus 1. So this is y minus y naught is equal to plus minus x naught. That's what the characteristic equation at x naught y naught is equal to. Okay. So finally, if we are looking at a parabolic equation, which again, remember the one thing that we did, del 2 del x squared minus del y psi minus b equal to 0. So this equation is going to be what? This equation is going to be given by a equal to 1, b equal to c equal to 0. Thus we have, so remember what these guys were. Yeah. So what you have is b squared minus ac is equal to 0. So this, of course, remember, is a parabolic equation. So the solution is dy dx is equal to 0, and which means that y equal to constant. So characteristic through y equal to 0. Oh, sorry, through x naught y naught is equal to, is just y equal to y naught. So for obvious reasons, what we are going to be doing that is that we are going to concentrate on the characteristics of the hyperbolic equations. If equations are simple, I mean, the equations are of course simple if a and a, b, c are all, I mean, just constants, and then these characteristics are just straight lines, and yeah, so that's what we will have. Um, okay, so now what we will do is we are going to look at this a little bit more, and we shall try to understand stuff, how to go ahead and understand these PDEs a bit more and find out how these things that we've learned right now is going to be useful. Okay, we'll see this a little bit more now. Yeah, so let's just try to see this once more. As we said, equations are simple. Um, equations are simple if a, b, c are constants. In that case, characteristics are straight lines. Or just straight lines. So here, you can just call y is equal to m1x plus c1, y equal to m2x plus c2, where m1, m2 are given by b plus minus root over b square minus ac by a, and c1, c2 are arbitrary constants. Okay. So that is why there's a family of them, because so these, given this slope, these are going to be lines which is these are two families of these lines. Okay. So we restrict ourselves to PDEs in two dimensions and that have constant coefficients. So these will be these will include, for example, the wave equation, the Poisson equation, the Laplace equation, and the Helmholtz equation in two dimensions. So let's just call these guys something. Let's call y. Let's call xi of xy. Let's call this y minus m1 x, and eta of xy. Let's call this y minus m2 x. Then the family of characteristics is just xi is equal to c1 and eta is equal to c2. So we can recast this, original PDE, for example, in terms of these eta or xi, or equivalently, we can also recast it in forms of something which we call x and y, which is xi minus eta twice I, and y is equal to xi plus eta by 2. So this is something that we can do. And in that case, so the various PDEs can be written in these following forms. So let's just look at first, say, if you want to look at hyperbolic, then this is written as del 2 psi by del psi del eta. So this is going to be given by some d prime of psi of eta psi eta. This is recast in this way, or equivalently, you can also write this as del 2 psi del x squared minus del 2 psi del y squared is equal to something which is psi of x, psi of y, x, y. If you are looking at elliptic PDEs, in that case, what you'll have is del 2 psi del x squared plus del 2 psi del y squared is equal to some, again, some d prime of psi x, well, psi y xy, and finally a parabolic equation there. As you know, psi is zeta is equal to eta, so you can choose y equal to zeta, which is eta, and x equal to x. Then the independent equation is going to look like then the equation is going to look like del 2 psi del x squared is just d prime of this guy again. So that's what we have now. So this is what we will do. Now, what we will do in these next few lectures, so now we have understood that characteristics are important things. So in the next few lectures, we are going to lecture 2, we are going to look at specific equations and see how you understand these equations from the term in terms of what we have framed so far. Okay, so that's what we're going to do. We're going to understand, we're going to try and understand the wave equation first, and then we will move on to trying to understand the one-dimensional diffusion equation, and finally the 2D Laplace equation, which is something that you guys are also familiar with. So that's going to be what we are going to do in the next next lecture or two. Yeah, so that's that for now. This was a bit, it was a bit short, but it was a very important thing for you guys to know that these this delta equal to 0, the thing that we had discussed last time around, as being the reason, as being an assumption of why what leads to the solution of these arbitrary second order differential equation in 2 dimensions. This this leads to something very important called these characteristic curves, and these we will see that these will show up everywhere. So in these the next 2 lectures that we will do, we will look at the wave equation, and then we will look at the diffusion equation and the Laplace equation, and try to understand this. Okay, so very good. So this is where we stop for the day now, and I'll see you guys soon.